This is ECE 343, Signals and Systems. This will be the seventh part of Chapter 4. Last time we introduced the idea of frequency response. In this lecture, we're going to do some examples of frequency response, some simple examples, and then we'll turn our attention to being able to sketch out both magnitude and phase response using pole zero information and do some examples on that as well. To begin our examples today, let's go ahead and look at an ideal delay system. An ideal delay system is one where the output y of t, right, is going to be equal to just a delay of the input, so x of t minus cap t. I'm interested in what the transfer function is of this system, so I go ahead and I Laplace transform that equation to give me y of s equals e to the minus st x of s. We know that a delay in time gives us multiplication by a complex exponential in frequency. That's one of our Laplace transform properties. The system function or transfer function, right, is just the ratio of output y over input x. And we can get that from that above equation just by dividing both sides by x of s. That tells me that the transfer function of this system is e to the minus s cap t. If I want to get frequency response from this, I just look at those values of s where sinusoids live right along the omega axis. So I substitute s for j omega, and I get h of j omega being equal to e to the minus j omega t. That is the frequency response of the system. Frequency response, as we know, is a complex function of the real variable omega that makes it a little bit difficult to plot. So it's most common to sit there and plot the magnitude response, so the absolute value of frequency response, as well as the phase response, which is the angle of frequency response. Let's go ahead and do that in this particular case. So I'm going to go ahead and look at magnitude, h of j omega. H of j omega, right, is just e to the j omega t. So I'm going to be looking at the absolute value of e to the j omega t with a minus sign in there. And we know that any complex exponential that has a purely imaginary argument, right, is just got magnitude 1. That's something we studied back in the background chapter. So this particular system has a magnitude response that's unity for all frequencies. What does that mean? That means that this system passes all input frequencies with the same gain, right? It doesn't matter what input frequency is put in, they all have exactly the same gain, a gain of 1, so they're basically unchanged in amplitude in making its way to the output. This should make some sense. If you look back at the original equation, y, right, was just equal to x delayed. If y is equal to x, we really don't expect it to be getting rid of some particular frequencies. You would expect any kind of frequency that went in would come out, right, as exactly that same frequency because y equals x. That would suggest that the magnitude response is a constant. If I look at the phase response is where everything interesting is happening with this delay system. So I look at the angle of h j omega, and that is going to be the angle of e to the minus j omega t. This was already in a polar form, and I know that the angle, right, for a quantity written in polar form is just going to be that thing, right, that e to the j, whatever it's multiplied by, that is the angle. So here we can see ej times minus omega t. So the phase here is minus omega t. That tells me that the phase response of this system, right, is a linear function of omega, right, whose slope is negative, and it varies based on the amount of delay. If there's more delay, you're going to get a stronger or higher slope, something along those lines. So I've just drawn it in here for some particular value. So this is the angle of h j omega. If I was really interested in maybe making this accurate, I could come out here to a value of 1 rad per second, come down to that guy, and what do I know what that would be? That would be minus t on that particular other axis, on the vertical axis. So this is a function of omega. So what we learn here is that when we have a phase response that looks linear, that's corresponding, or it can be interpreted as some amount of delay in the input. So constant magnitude coupled with linear phase just means that a signal is going to get delayed. If I look at an ideal differentiator, this will be my second example. An ideal differentiator has an output y that is just going to be the time derivative of the input. Again, I want to find the transfer function, so I Laplace transform that. That gives me the expression ys equals sxs. The transfer function h is just ratio output to input, and so that's going to be s. Frequency response, you let s equaling j omega, so h of j omega equals j omega in this case. Remember, frequency response is just looking at those values of frequency s, right, where sinusoids live. And we know that sinusoids live on the omega axis. In this particular case, I'm again interested in looking at magnitude and phase response. Let's go ahead and take a look at magnitude response first. So in this case, magnitude response is magnitude h of j omega, right? And that's just going to be magnitude of j times omega. The j there doesn't contribute anything to the magnitude. We know magnitude of the product is product of magnitudes. So magnitude j omega is going to be magnitude j, which is 1, times magnitude omega. So I'm going to get 1 times magnitude omega. So this is just going to be absolute value of omega is going to be my magnitude response. I can go ahead and plot that. And so we get something like this, where we have our horizontal axis being omega, and the vertical axis is my magnitude response, magnitude h of j omega, and we are getting something, right, that grows linearly with omega, right, in an absolute sense. And we do see that this guy's got a gain of 0 at DC. We'll come back to that when we think a little bit as to whether this magnitude response makes sense. We're going to go ahead and do phase response as well. So the angle of h j omega, right, is equal to the angle of j omega. Well, two possible cases there. When omega is positive, right, then we have j times a real number, and the phase of that is pi by 2 or 90 degrees. So I'll get pi by 2 for omega being greater than 0. When omega is negative, right, then we're going to get minus j, and the phase will be a minus pi by 2 for omega less than 0. We don't really care too much at omega equaling 0, because if you look at the gain or the magnitude response at 0, it's 0, and so the phase won't matter because nothing can get through anyway. So let's go ahead and plot this guy out as well. So as a function of omega, I'm looking at the phase response angle of h j omega. And in this particular case, I'm going to get a positive, right, pi by 2 when frequency is positive, and I'm going to get minus pi by 2, which is minus 90 degrees, so minus pi by 2 for any negative frequency. So let's think a little bit about this. One of the first things that we might just try to focus on is this idea of the gain being 0 at 0, right? What is this telling us? It tells us that DC signals will not make it through this system, right? Their gain is 0. Of course, we know that, right? Because if you differentiate a DC signal, that's differentiating a constant. And we know differentiation makes a constant go to 0. So that's something you saw back in calculus. It's something that's very intuitive. You take a DC signal or a constant signal and you differentiate it, you get 0. So the gain is 0. If I wanted to figure out the rest of it, I might just think of a sinusoidal input. So let's go ahead and look at x of t being equal to cosine omega t. Y of t then, right, is just going to be equal to the time derivative of that input, so time derivative of cosine omega t. And if you remember back to trig in this particular case, right, we know that we get a minus. We will have sine omega t, so cosine differentiated gives us sine, but then you have to also differentiate that argument of the sine, so take the derivative with respect to t of omega t. That gives us an omega out front as well. So take a look at what happens in this particular case. In this particular case, right, we have that factor out front minus omega. So the strength or the size of this signal gets amplified by whatever the input frequency is, proportional, right? If you have sine of 100t or a cosine of 100t, it comes out as 100 times sine of 100t. That's that linear gain, right? That linear gain that we have in there. If you come out to some omega, right, your gain factor out there is the same amount omega, and it's because of that omega term that we saw through differentiation. The phase in here, we know cosine and sine are related by a 90-degree phase shift, and with that minus sign out there, it is a plus minus 9, it's a plus 90-degree phase shift. So hopefully this simple cosine input further provides some confidence in this magnitude and phase response plots that we get. So magnitude response for an ideal differentiator, right? It looks like this V-shaped curve. So we have that V shape because it's a linear gain as a function of frequency, as we saw here, that linear gain, right? And we know that when you differentiate a cosine or a sine, right, that we get a 90-degree phase shift coming in. So cosine going to minus sine is a 90-degree phase shift. If I look at the kind of inverse of a differentiator or an anti-differentiator, that's an ideal integrator. So we're going to go ahead and look at an ideal integrator. In this particular case, our output y is just the integral of x. If I want to find the transfer function, I'm going to go ahead and Laplace transform that guy. So we go ahead and do the Laplace transform on that, and I get y of s equals 1 over s x of s. These are just properties of the Laplace transform again. Of course, we kind of knew this. If differentiation was s, right, and integration is the antiderivative, we should get a 1 over s in the transform domain. That means the transfer function, output over input, is just 1 by s. It's 1 over s rather than s. And my frequency response, let s equal j omega. We have h of j omega being 1 over j omega. So let's go ahead and take a look at what this guy looks like in magnitude response and phase response. Magnitude response, magnitude of h j omega, right, is going to be the magnitude of 1 over j omega. Again, the j doesn't contribute anything, and I'm going to get 1 over magnitude omega. If I take a look at that guy, right, we get a 1 over omega in absolute value kind of term. And so if you put 0 in there, that thing flies off to infinity. So it goes asymptotically to infinity at 0. And as omega becomes big at either plus or minus infinity, it goes down to 0, something like that. So you get this almost reciprocal kind of gain term, right? So this is magnitude h of j omega as a function of omega. How about that infinity kind of gain that we would expect at a frequency of 0? Well, what happens when you integrate DC? If you take a DC signal 1 and you integrate it, what does that mean? That says, what's the area of the curve, which is 1 for all time? So how much area is there for a signal that is 1 forever? Well, that's infinite area, right? So we'd get an infinity out of there. That's that infinite gain again. And if you want to think about this in a reciprocal sense, we know that the gain of differentiation at DC was 0. This gain of integration at 0 is going to be 1 over that, so that's going to go out to that infinity. In fact, if you cascaded an integrator with a differentiator, the overall net should be something that comes out basically undistorted. Let's go ahead and take a look at the phase response. If the phase response is kind of compensation for that differentiator, if you go back and look at what we had differentiator, we had a 90-degree phase shift for positive, minus 90 for negative. We would expect those two phases to flip, right? So that's exactly what will happen here. So if I look at angle of h of j omega in this particular case, right, that's going to be the angle of 1 over j omega. Now, if omega is positive, then the angle is based on a 1 over j, which is a minus pi by 2 for omega being greater than 0. If I go ahead and I look at omega negative, then the angle is based on a 1 over minus j. That is pi by 2 in angle. That's for omega less than 0. If I go ahead and plot that guy, right, plot this guy in here, we're going to have that minus pi by 2, right? So minus pi by 2 for omega being positive. We're all doing this for the angle of h j omega. And we know that we get pi by 2, right? Pi by 2 for negative frequencies. And it's what we would expect, right? It would undo the 90-degree phase from a differentiation. You'd get a minus 90 in compensation for a 90 and vice versa for the positive and negative frequencies. You could again do this through putting in a cosine and looking at what happens when you integrate a cosine. You integrate a cosine, you get a minus sign, for example, and we know that we can get those same sort of ideas, but it would be scaled by 1 over omega, right? Because it's integration. If you did that. So I'll leave that as an exercise to you, but it's essentially the inverse system. If you look at h for a differentiator, right, that was s, and h of an integrator was equal to 1 over s, something along those lines. We see that that's 1 over hd. The other thing that we see is something like this, like if I did an integration followed by a differentiation, right? That's a cascade operation that I could do. I know that things in cascade, their transfer functions multiply. So what would I get? I'd get a 1 by s times s. That should just be 1. So if I integrate and then differentiate, I should just get back my original signal, probably within the original DC constant. So there's an argument to be made there, which we'll not delve into too deeply. Let's switch gears right now. So what we would like to do, this is really one of the last topics of this chapter. We're going to go ahead and figure out if we can sketch out frequency response using pole and zero information. The past 3 examples that I did were all relatively simple. I didn't really need a lot of kind of fancy mathematics in order to get pretty good sketches. They came out just really directly. As we get more complicated or sophisticated transfer functions, things that involve polynomials of much higher order or rational functions of much higher order, it can become very difficult just to look at it and say what's going on. So we'd like to look at methods for sketching this out. We already know we can do it with MATLAB. If you have a computing tool like MATLAB available, you can get very accurate plots at low cost, but there's some value in just being able to do some hand calculations as well. For us to figure out how to get frequency response from pole and zero information, the basic technique is that we first start with the transfer function and we represent it in factored form. What's factored form? You root out the numerator and you root out the denominator, right? And you write it as a product of factors. So I would have h of s being represented as a product 1 to n of s minus zk. Zk's are the zeros of the system. They're the values of s, right? The roots, basically, of that numerator polynomial. And they're the values of s which force that numerator to 0. If you remember, h of s is kind of that gain factor for an everlasting exponential, right? If you put an e to the st into a system where s matches a 0, that system's going to kill that, right? So systems tend to minimize or to make smaller inputs that have a frequency close to that 0. We'll see this focused on or emphasized a little bit later. The bottom factors, right, are also just going to be a set of roots because we have a polynomial generally for h of s, at least if it came from a constant coefficient linear differential equation. So the denominator is going to be a bunch of potential roots in there, and we'll just factor that out. And those factors are called the poles of the system. And so the factored form for that is a product 1 through n of s minus the poles pk. And I've just drawn these using a little bit of color coding. So I'm going to use green for the zeros and red for the poles. We also have an overall constant out front. That's because the lead coefficient for the feed forward terms, the ones that are based on the input, that one that multiplies the highest power of s is not normalized like it is in the denominator. So you have an overall B0 as well. That just imparts just an overall gain on all of this. Okay, so we have a transfer function that's written in factored form. If I make this into frequency response, I can do that simply by just letting s equal j omega. So you get the same exact expression. It's just s has been turned into j omega. That is frequency response. So at this point, it's not too obvious how that's going to help us. We know that frequency response is a complex function of frequency, and that generally what we would prefer to look at is magnitude and phase. So let's go ahead and take a look at the magnitude response from this factored form of the frequency response. So the magnitude response, right, is just the absolute value of hj omega. Well, that's going to be the absolute value, right? We're going to just take the absolute value of this guy. So we need to do the absolute value of a product. So absolute value of a product is just the product of the absolute values. So when I take the absolute value of that expression h of j omega, I'm going to get the absolute value of b0, and then I'm going to get the absolute value of all the terms j omega minus zk multiplied together, and I'm going to get the product, right, of the absolute value of j omega minus pk. So all those guys multiplied together as well. So this gives us something that's broken down into maybe little simpler pieces. We're going to deal with each one of these little absolute values by themselves, and then just take all those numbers and multiply them together. And the denominator terms, of course, have to get divided out. I think what can help us in this particular case is to get a sense, the absolute value of a constant, that's easy. We don't have to worry about that. It's trying to figure out what do we mean by the absolute value of j omega minus zk, or the absolute value of j omega minus pk. Zk and pk can be complex, and clearly j omega is complex. So we'd like to think about what is the absolute value of a difference of some complex numbers. We can do this graphically, and I think this graphical kind of interpretation, or this graphical view, is going to be really, really helpful for us to understand how we can quickly make an estimate of magnitude response based on pole zero information. So graphically, what is meant by this term absolute value j omega minus zk or j omega minus pk? They're the same thing. It's just in one case you're going to multiply by the number, and in one case you're going to divide by the number. Let's go ahead and take a look at the case of j omega minus zk, just doing this purely from convenience. So zk is some number in the complex plane. I've drawn that in this case by using a little green dot. So that green point right there is some value. It's the 0 of my system. Because it's a complex number, you can think of that in a vector sense. So I've drawn that vector, right, as this green vector that goes from the origin to the point. So we know that a point in the complex plane can be represented in a vector style where we go from the origin to the point of interest. We can do the same thing for j omega. J omega is just a frequency of interest. So I've gone ahead and shown this in blue. I've just picked a particular frequency of interest. I've made this a positive frequency. because we think of j omega as that thing that goes on the omega axis, right, that vertical axis, we're just going to go from the origin up omega units, right? And so that's also a vector. It's this little blue vector. I haven't made it very far up on that. And so that's my j omega. We now need to add two complex quantities together. You've done this before in math classes. When you have two vectors and you want to add them together, you can add them together head and tail. There is that minus sign in there, right? So what do I need to do with that minus sign? That minus sign is going to require me to negate, right, or reverse the arrow direction of my original zk vector. So I've shown that in this particular case as this other vector, and I put that guy right head to tail to the original vector that I was basically adding that to. So I took j omega, that's the blue one, right? Subtracted off the vector zk, which means I just reverse the direction of that zk vector, and I hook it on head to tail. So you add through head to tail, right? And it's just one of those vectors got turned the other direction because of the minus sign. What that results in, right, is a point. It's this point right here, that yellow point, which we could also interpret as a vector. That vector has a size, so a distance or a magnitude. It also has an angle, right? So this vector, j omega minus zk, I've shown. And what I'll notice is that that vector that is there, right, has the exact same orientation, size, and angle as the one up here. And I think the one that's shown up here that I have labeled as same length as j omega minus zk, it's also the same angle as j omega minus zk, is just a little more convenient because it's a very quick way of figuring out what it is that we're trying to measure when we look at magnitude j omega minus zk. We're basically taking a look, right? We're just taking a look at this vector going from the root, whether it's a pole or a zero, to the frequency of interest. If I'm talking about the magnitude response, I'm just saying what's the length of that vector. So frequency response, right, involves all of these guys that are like j omega minus zk's and j omega minus pk's. If I'm looking at the magnitude response, it's the same difference of terms, right? But now we're just looking at the size of them, so the length of those vectors. So magnitude response in this particular case, a magnitude response is only going to be really interested in the distances from roots, whether they're poles or zeros, right, to a frequency of measurement, some particular omega. And we usually do that for a whole bunch of omega, so we can get a nice plot for our magnitude response across all frequencies of interest. You might do that for quite a few frequencies. So what do we get in the end? We have this magnitude response, h of j omega, absolute value, right? It's going to have some overall kind of gain factor based on that coefficient b0. And then I'm going to have a product of what? A product of distances going from the zeros to the frequency of interest. So a product of distances from the zeros to the frequency of interest. That's in the numerator. And in the denominator, I have a product of those distances, right? A product of the distances from the poles to the frequency of interest. That's it. So if you have a ruler and a pole zero plot for your system, you should be able to estimate magnitude response just by measuring a bunch of distances, multiplying some numbers together, dividing some numbers from that, and then just recording those values. The magnitude response, right, this magnitude response, it depends on the lengths of vectors going from either poles or zeros to a frequency of interest. And you repeat that for all the frequencies that you would like to make your plot for. A couple of things to note or consider on this. If we are close, so if the frequency of interest is close to zk, what does that mean? That means that this distance in the numerator is small, right? And if that thing is small, that means that the magnitude response gets small. So if you were at a frequency that is near a zero, right, your overall magnitude response is going to reflect that by being small. Zeros tend to suppress or weaken inputs of frequencies that are near those zeros. Zeros have a minimizing, a weakening, right, an attenuating kind of effect on inputs. If you look at the poles, if you have a frequency that is close to a pole, that denominator distance, right, gets small, but because it's in the denominator, 1 over a small number becomes big. That means the magnitude response acts reciprocally to that small distance, so it's going to get large. If you have an input frequency that is near a pole, that pole wants to boost or make the response to that particular frequency stronger. So poles boost or strengthen inputs. Poles and zeros do exactly the opposite things, right? Poles make bigger, zeros make smaller. If we take a little bit further look and we think about frequencies that are really, really far away from a pole or really, really far from a zero, then the difference there is approximately just the omega. What does this tell you? If I take a look at that, the absolute value of j omega minus either a pole or a zero, if that omega is really, really big compared to zk or pk, well, then we're just going to have that size basically be equal to magnitude omega. What does this tell us? This tells us that the magnitude response is essentially unchanged. It's unaffected if we're looking at frequencies that are very far from poles or zeros. Far away poles and zeros have almost no impact, right, on the overall magnitude response. If you're really, really far away from a pole or a zero, you can mostly just ignore their effects when it comes to magnitude response. Okay, phase response. We can do all of this again for the phase response as well. It's very similar. I'm not going to go through all this in the same way. You can read this in the book if you like. It's all the same basic stuff. It's just now instead of those magnitudes, we're going to be measuring angles. And I'll do an example so you'll be able to see this working. The phase response, which is the angle of hj omega, is going to be the phase of that factored form. And we know that phases, right, when we multiply a bunch of things together, if I write them in polar form, all the phase terms of those guys add, right? That's just a consequence of polar form. If I have two terms multiplied together and I write them both in polar form, you would get something like an re to the j omega or re to the j theta, and then you'd multiply that by another one like an r2 e to the j theta 2, and the size of that's going to be an r1 r2, and the angle is going to be a theta 1 plus theta 2. So the phases add. So what is the phase response on this? Well, it's going to be the phase response of that factored form. We saw that. But what we get is we get basically the phase of B0, and then we're going to add all the phase components in going from the zero to the frequency of interest, and we subtract from that because it was in the denominator, a sum of all the phases going from poles to the frequency of interest. Again, this is derived in the book. It's really just a very simple extension of what we already saw in detail for the magnitude response. What I think will be helpful in all of this is just to go through a detailed example where we can do both magnitude and phase response. In the end, it's very simple to estimate either one. Magnitude response, we get out our ruler and we measure a bunch of distances, right? Phase response, we're going to have to measure some angles, but then we just add or subtract those angles. So hand sketch, let's do this as an example. Let's hand sketch both the magnitude response and the phase response using this pole zero information for a system, h of s, right, that can be represented as a half times the quantity s squared plus 1 over s plus 1 half quantity squared. If I factor that guy out, I see that I get a half s minus j s plus j, and I get an s minus of a minus 1 half quantity squared. That means there's a pair of poles at exactly the same location. So this guy right here is that factored form, right? We got that guy as a factored form. We can do this as, and if I was going to be really, really maybe completely correct here, maybe I would do minus of a minus j on that one, something like that, just so we can easily tell where the poles and zeros are. Okay, so I have a transfer function and it has some poles and zeros. Every single time it's going to be a handy deal to go ahead and draw out where are the poles and where are the zeros. I'm going to follow the same kind of coloring convention that we were doing above. So I'm going to draw the zeros in green and I'm going to do them as green circles. We can see here that I have zeros at plus and minus j. So I'm going to go ahead and put 1 0 here, right? And I'm going to have that at what was basically 1 unit. That's the j1, I guess, if I was going to be 100% mathematically correct. That's 1 unit up on the imaginary axis, right? And then I have the other one sitting down there, minus 1 unit on the vertical axis as well. So that's reflective of the minus j term. So I've got a pair of zeros, and they lie on the omega axis. My poles, I'm going to do in red, and I see that I have a pole at minus 1 half. And so I'm going to go ahead and put it in here at minus 1 half, but it was repeated. So I'm going to put a little 2 in there just so that I know that that thing has been repeated twice over. If I wanted to give just maybe a little bit more in here, I know that that guy out there to the left would be something like minus 1. This is in the complex frequency plane, right? And so we're just marking out, you could call this the S plane. We have this guy over in the S plane, something like that. And I'm just doing a pole zero plot. So this guy sitting over here is my pole, what is called my pole zero plot. It is just a plot in the complex plane that shows the locations of the poles and zeros. Okay, I'm going to make multiple copies of this. Let's just start with one, and because we're going to use it quite a bit, so let's go ahead and copy that guy. And I'm going to come over here and I'm gonna paste it in, just so that we have a copy of this. Think about what frequency response means. Frequency response means that I pick a value of frequency omega that's on that omega axis, right? And so I'm going to run a value omega back and forth or all over that axis, right? So that blue line reflects the different values, right? That blue line, if I wanted to think about that, those are the values omega I'm interested in. I'm interested in using, right, to compute both my magnitude response, magnitude h of j omega, and my phase response, angle h of j omega, something along those lines. So as I move my omega all over on that guy, I'm going to just be measuring some distances from various points, the poles and zeros, or from those poles and zeros to that frequency of interest, measuring those distances, or measuring the angles, and either multiplying and dividing those numbers, or adding and subtracting, depending on whether I'm doing magnitude or phase. Okay, so let's work on magnitude response first. And again, I'm going to do a bunch of copies of this. So I'm going to come back down here and I'm going to recopy that guy in, and I'm just going to leave it here for a second. And we will start working on the magnitude response. So let's work on the magnitude response. We want to know how this system, right? How this system is behaving as a function of frequency. Actually, you know what? I might even do something a little different on that. If you look back at this pole zero plot and you remember our basic observation, that as frequencies near zeros, right, the overall response gets smaller, and as the response or frequencies get near poles, the response gets bigger. If you take a look at that frequencies that I look at, what is this frequency right there at the origin? Let's do this in a darker one, right there at that origin. That's DC, right? DC is about as close as you can get to the pole. So I'm expecting those poles to kick in and give me a pretty strong value at DC. As I move that DC away and I start heading up here, I'm eventually going to hit that pole or that zero. When my frequency hits that zero, I know that that zero is dominating and it's going to make the response really, really tiny. So we're going to go from a pretty big gain at DC to a very small zero gain actually when I hit 1 rad per second. And as I get further and further away, I should be seeing less and less impact from either one of those guys. So I should get a pretty big bump near DC, get some attenuation, serious attenuation near plus or minus 1 rad per second, and then I should just kind of level out for higher frequencies. Let's get a sense and see whether these calculations support that. So we're going to be looking at magnitude response. I want to look at magnitude h of j omega, and I would like to be able to plot this guy. So I'm going to go ahead and draw my axis in here, and we're going to do a bunch of calculations to try to put in values here. So I'm going to look at different values of omega, and I'm going to be looking at magnitude h of j omega. And I'm going to use this pole zero plot and a bunch of others to see if I can do it. Usually what you do is you just start picking some values and you start doing your measurements. So let's start with the DC response. Let's look at omega equaling 0. Omega equaling 0, the first thing I probably want to do is I want to find out what is that B0. B0 is 1/2 here, right? That is my B0 in this case. So I could have written that over here as well. I could have said B0 equals 1/2, right? Something along those lines. At omega equaling 0, right, what do I get? I'm going to have magnitude h of j0, right, being equal to magnitude b0, right, times a product. This is going 1 to 2 because there were 2 zeros, right? And I'm going to have the magnitude of j omega minus my zeros. And then I'm going to have a product 1 to 2 of my distances from the poles to the frequency of interest, something along those lines. Okay, so we know what the basic formula looks like. I know that for every single one of these guys, this guy's just going to be 1/2. We get that because we can see that that B is 1/2. What we need to do is we need to make these calculations of these distances. So let's go ahead and do that in this particular case. I'm going to start by doing my omega equaling 0 calculations here. What do I need to do? I need to measure from the zeros to the frequency of interest. What's my frequency of interest? It is omega equaling 0, right? So there's my omega equaling 0 point. And I need to measure some distances. What's the first distance I need? I need it from the first 0 to that frequency. Well, that's a distance of 1, right? And I can go from the other 0 to that point. that's also a distance of 1. So when I think of h of j 0, I'm going to get, I had that half from the b0, but then I'm going to get a 1 times 1 because of the distance from each 0 to that frequency point of interest, which in this case is omega equaling 0, are each 1. In the denominator, what am I going to do? I need to go from the pole to the frequency of interest. That's a half, but there's 2 of them, so I'm going to get a 1/2 times a 1/2, something along those lines. So that's going to be 1/2 times 1 divided by a half divided by a half. That should give me a value of 2. So this thing has a DC gain of 2. I'm going to go ahead and draw that in. I'm going to come up 1, 2 units, and I'm going to put in my overall gain there. So I get a gain of 2 at that point. The other thing that I can do in here very quickly, right, is I can go ahead and look at omega being equal to plus or minus 1. This is almost trivial because magnitude of h of j plus or minus, whoops, let's just do that a little bit more clean mathematically. Let's do that as a plus or minus j, right? That's j times 1. Frequency here is 1, is equal to what? Well, we are going to still have that 1/2, right? We're going to have a 1/2 in there. And then we would also have in this particular case, if we were going to look at it, we would also have in this case the distances going from the poles, which aren't going to really matter. And then we're going to have the poles, the distances from the zeros. Why don't the distance from the poles matter? Because the distance from the 0, one of them is going to be 0, and that's going to make 0 times something, and it's just going to be 0. So let's go ahead and maybe recopy that overall graph, and we'll look at it down here as well and make sure that we can handle that, guys. So I'm going to go ahead and look at this. Oh, and let's just not make it so confusing. Let's just do plus for right now. So let's just do the plus 1. Okay. So what are the distances that we're looking at here? I'm going to go ahead and do green first, right? The distance from one of my zeros, right? It's just, whoa, that was not the right one. One of my zeros in this particular case is going to be just a distance of 0. So if I look at this first one, right, the distance there, the distance is 0 because my frequency is 1, right? My frequency is 1. I probably should have put that as a blue dot. The distance from that first or upper green circle to that blue dot is 0. So our first distance is 0, and I'm going to get 0 times. And then what's the distance from the other one? Well, it's 2, right? I had to go across 2 units there. So it's 0 times 2 over. And then I look at the distance from the poles, right? I'm going to be going up there over 1/2 and then up 1, right? So that's going to be like a half squared plus 1 squared. That's 5/4 square root. So that's going to be a root 5/4. But there's 2 of them, so that's root 5/4 2 times over. Like I said, none of those particular calculations were terribly needed. Why not? Because of that 0. That 0 is going to dominate this one. We're going to get 0, which also happens to be the magnitude of h minus j because of the same sort of symmetric geometries that are in there. So let's go back up here. Let's come over here to a frequency of 1 rad per second and minus 1 rad per second. And what do I know? I get zeros. And in fact, this is a really easy one. Anytime you see a 0 right on the omega axis, you know your overall gain is going to be 0. Those are freebies. You just come in there and you draw them on and you're done. You probably don't even have to do the supporting calculations. This is not a terribly complex system, so I could probably make a rough sketch right now, at least for those frequencies between -1 and 1. I do want to think, though, about what happens as I get to higher frequency. So let's go ahead and look at the case of omega tending to like infinity, something along those lines. So I'm looking at the magnitude of hj infinity, if you will, something along those lines. I'm going to go ahead again and plot out my graph here so I can work with that guy. So I'm going to have this graph over here just so I can use that as a reference, okay? And I'm going to try to think about the distances again on this guy. So the first one is going to be what? It's going to be that 0 going to some guy out there at infinity. So what's that distance? Well, I'm going to do this in a really rough sense. So we know this whole thing equals, right? Oh, and I guess I did not yet put in my B0 values. That's still a half. But now I want to work with what's that distance from that 1, 0 to the other guy. Well, that's like an infinity minus 1. It was already 1 unit up because of the 0 being 1 unit on the north side of the graph there, right? And we went out to infinity, so the distance there is maybe infinity minus 1 if you want. What's the other one? It's like infinity plus 1. And what is the distances from my poles? Well, when they go out to infinity, they're basically pointing straight up and they're going basically infinity. infinity. So on the denominator on this guy, you could think of it as going, being divided here by like an infinity and infinity. This is loose mathematics, but basically the numerator goes out to infinity at the same rate as the denominator goes out. Those guys basically cancel out, and we are going to get in the limit 1/2, right? It's all dominated by that b0 term, something along those lines. You could have done it in a slightly different way, probably the more mathematical way for those who want to do it mathematically. You'd do something like this, maybe as a limit, right, as omega goes off to infinity, and we had a half, right, and you had something that was going to be basically a distance of omega minus 1 and omega plus 1 and an omega squared, basically like that. In the limit as omega goes off to infinity, that's going to be equal to a limit as omega goes off to infinity. Again, I don't think you have to do this, but we're going to have a half, and I'm going to have what? I'm going to have, I'm going to have omega squared, and then I'm going to have minus 1 over omega squared, something like that. This minus 1 doesn't matter at all when omega is going out to infinity, and so I'm just going to have omega squared over omega squared. That's just 1. That whole thing then just gets multiplied by that 1/2 out front, and I get 1/2. Exactly what we said. Okay, so this is true actually for plus infinity, and it's also the same thing that we get for magnitude h of minus j infinity in this particular case. Because of why? Because the symmetry going this way is the same as the symmetry going that way. The distances going 1 unit up is going to be the same as the distances going 1 unit down, or 10 units up or 10 units down, or 1,000,000 units up and 1,000,000 units down. This tells me, because of the symmetry of my poles and zeros about this horizontal axis, right? Because of the symmetry between there, what do I know? I know that the magnitude response, that magnitude h, is going to be even in symmetry because of this symmetry in my poles and zeros about that horizontal axis. Okay, so I've gone through and I've calculated those out as being a half. And I'm going to come back up here and I'm going to think about that. So half is somewhere in here. And I'm just going to put some dotted lines because I know it's going asymptotically to this as I get really, really large out there, something along those lines. And now I think I'm probably good to go ahead and sketch this out. We know that this thing's going to come down, right, and hit that 0. And then it's going to come back up and it's going to work its way to infinity. Because this is a second order filter, it's really not going to have much more exciting stuff going on in here. Are we perfectly correct? No. We're good at 0, we're good at 2, we're good at this other 0, and we're good at those values of 1/2, right? The rest of the stuff, we'd probably have to do more calculations if we were going to have it perfectly good. But in general, we have an overall idea, and this matches with what we expected. Low frequencies were near the poles, so we got a boosting or pole effect in there. So I'm going to go ahead and do that in red, right? That's when we're really near the poles, and so we get something coming out bigger. And then when we get near the zeros, we get smaller, right? And as you get far away, neither of the two come into play, and so we end up just getting that b0 term coming in as being the dominant force in this particular case. So it turns out to be rather intuitive. Maybe during the recitation, we'll go ahead and do the MATLAB version of this, and we'll be able to compare this rough sketch to the more accurate MATLAB plot. We'll find out it lines up really, really good. So we've been able to do the magnitude response just by measuring distances from poles and zeros and taking ratios of those products of numbers. So pretty straightforward. Let's go ahead and finish this example out, and let's look at the phase response. So I'm going to look at the angle of h j omega. And we said that this was the angle of b0, right? And then we are going to have a plus sum, because there's only 2 zeros. It's going to be a sum from 1 to 2, right, of the angle of j omega minus our zeros. And then we subtract off the angles, going I equaling 1 to 2, because there's only 2 poles in there, of the angle j omega minus the p's, the poles in there. Okay, so we want to be able to try to figure out the phase response. Again, we're going to try to get a graph here. Because of the symmetries here and the way phases work out, we'll find out that the phase response ends up being an odd function of omega. So I'm going to go ahead and try to draw my axis reasonably accurate here, and I'm going to make it go deeper down. Magnitude response, right? Because it's magnitude, it better never be negative. You absolutely should never be getting anything down here, right? Magnitude response is always positive. For phase, because it turns out to be an odd function of omega, you're going to get some cases that are both plus and minus, and so you'll probably need a more balanced graph. So we're going to be looking at angle h of j omega in this case. Okay, so we can do the same sort of thing. We can start trying to measure angles, right? And we can do so for a variety of points. Maybe starting out at the DC would be a good one to do. So I'm going to plot back out my pole zero. You're going to make a lot of use of these pole zeros. This method really depends on you using the poles and zeros, right? And so I'm going to be looking in this first case of the angle of HJ0. I want to look at the DC phase. So that tells me what? I'm looking at this frequency at omega equaling 0. So I'm right there at the origin. And I need to measure some angles here, okay? The first thing I'm going to note on this was that what? B0 was equal to a half. That means the angle of B0, the polar form of a half is just a half e to the J0. So the phase is 0. So the angle of B0 is equal to 0. So if I'm finding out this phase response and I start out with that B0 term, I'm just going to get a 0. So that one's not too exciting. Then I'm going to add what? I'm going to be adding in the phases, the phase contributions due to the zeros. And what do I need to do? I need to measure the angles going from the root, the zeros, to the frequency of interest. So let's go ahead and try to do that. So I'm going to come over here and I'm going to look at that first 0 at 1, right? And I'm going to draw a vector going from that guy to the frequency of interest. This one happens to point straight down. When I measure the angle, I always measure angles relative to the positive real axis. So I see here that the angle here is minus pi by 2. It's a minus 90-degree phase in this particular case. And if I look at the 0 at minus 1, and to get to the frequency of interest here, 0, right, I'm going to be pointing straight up. And if I measure that guy's phase, I'm going to do that relative to the positive real axis again. So here's the phase of that vector. That is going to be pi by 2. So my two angles here are going to be, in this particular case, minus pi by 2 plus pi by 2. They happen to cancel out, okay? And then I have to do what? I have to be willing to subtract, and I'm going to subtract on this particular guy. The phase contributions due to the poles. So I need to be able to come in here and measure the angles of the poles. Both poles are in the same location, so they're both going to contribute their same phase amount. Where is the vector going? It's going from the pole to the frequency of interest, and there we see that it moves directly horizontal from left to right. Measured against the positive real axis, that's a phase of 0. So I'm going to get 0 plus 0 because there were two of them. If I do all of those calculations, I'm going to have 0 minus pi by 2 plus pi by 2 minus 0 minus 0. That whole thing comes out to a big fat 0. So this was a lot of calculation just to find out I get no phase. So I have a phase there of 0, something along those lines. Let's go ahead and go out to the extremes of plus or minus infinity, and so we'll go and do those as well. So let's go ahead and plot that pole zero plot again, and we're going to think a little bit about looking at the phase response at, let's say, infinity to start out with here. So I'm going to look at the angle of HJ infinity, and that's going to be equal to, and in the first case, I'm going to get 0 again. That's no problem because the b hasn't changed. That's always going to be 0 in this particular case because it was a positive real number. And then I need to add in the phases from the two zeros, and I'm going to subtract off the phases from the two poles. So let's go ahead and measure those angles going from the zeros to infinity. First 0, they're at 1, going out to infinity. That guy points straight up. That second 0, minus 1, going out to infinity, points straight up. If I measure the angles here, right, that angle there is pi by 2. This angle here is pi by 2. So I end up getting pi by 2 plus pi by 2. That's a total of pi. If I look at the same thing for the poles are out there 1/2 unit to the left, right? But then they're pointing towards infinity, and that essentially just points them straight up. 1/2 compared to a length of infinity, that angle there is going to be pi by 2. And there's two of them, so I'm going to get pi by 2 plus pi by 2. Two poles are each contributing a 90-degree phase. So if I go through and calculate that, I'm going to get 0 plus pi minus pi is again 0. Okay, so this seems really, really boring. If I come out here, I know that as I come out here, I'm going to be coming close out to 0, something along those lines. Let's go ahead and take a look at the other side of this, and we'll go ahead and plot this thing out again and very quickly do this next one going to minus infinity. So I'm going to go ahead and look at the angle response of h minus j infinity, and it's going to be something doing due to the zeros and subtracting from that. So I should have made that a minus sign, and we're going to subtract to that something from the poles. I know that there's the overall phase of the B0 coefficient, which in this case is 0. And now I just have to go ahead and measure my angles. Okay, From the 0 at 1 going out to minus infinity, it points straight down. Same thing with the 0 at minus 1, straight down. What are the angles there? That's minus pi by 2, and we are going to have another one, minus pi by 2. So I should get here minus pi by 2 and minus pi by 2, something along those lines. And then I'm going to be doing what is the poles, and the poles are both pointing straight down, and they, relative to the positive real axis, are again going to be minus pi by 2. So I'm going to have a minus pi by 2 and a minus pi by 2. So I'm going to have minus pi minus a minus pi, so that's going to be minus pi plus pi. Oh, we went through all that again, and we got out a bunch of zeros. At this point, this thing is seeming really kind of boring. We had 0 DC, and we have 0 out there at plus and minus infinity. It seems like this thing's not doing a lot of anything. We might try, just like we did for the magnitude response, to think about stuff at plus and minus 1, right? We could think about plus and minus 1. The problem with this has to do with what happens if I pick. So let me just go ahead and do this. Let me put a value of 1 in there, okay? The angle from that 0 at 1 to the location 1 is undefined, right? Because there's no vector there. The vector has 0 length. We can't get an angle measure for it. So we get into trouble if we pick something that aligns exactly on a 0. What we can do, though, is we can look just a little to the left and a little to the right. I'm going to do this around the frequency of 1. I'm going to get a couple of values, and that'll be enough for me to finish out the plot. And then I'm going to rely on the oddness of the phase response to do the other half of the side. So let me come down here, and I'm going to draw or put down 2 more graphs for myself, just like we had from before, because we're going to look at basically 2 different values here. So there's one of them, and I'm going to put out another one for when I do the next one. And what I'm going to start by looking at is I'm going to look at the angle of what I'm going to call h of j, and I'm going to go 1 minus, just a little bit before 1, just a little bit before 1. Let me draw that. I'll draw it exaggerated, right? It's just a little bit before 1. If I think about what this is going to be phase response wise, if I think about what this guy's going to be phase response wise, I'm going to get the phase from B0. That's still 0. I'm going to add a couple of phase components, and I'm going to subtract a couple of phase components. Okay, let's go ahead and try to figure out what those particular values are. I'm going to do the zeros first, and if I look at that value 1, right, because that blue point, the frequency of interest, is just a little bit short of it, that guy, I'd have to zoom in a little bit, that guy's going to be pointing straight down, right? And the one from below is going to be pointing straight up. So the angles there are going to be what? They're going to be minus pi by 2 and a plus pi by 2. Something along those lines. So if I'm just not quite to that frequency 1, my phases, the phase contributions due to the zeros, the first one is going to be that minus 90, right? The second one is going to be that plus 90. So those guys are going to cancel. They're not going to come into much play. What about the poles, though? The poles sit there, go, and they have a distance 1/2 there, and they have a distance of 1 there, because we were just barely underneath that. So we can make that as close to it as we want. And so I need to find the angle, right, for a triangle that has an opposite side of 1 over an adjacent side of 1/2. So that's like the an arctangent function. You can go ahead and go through that particular arctangent function. Both of these guys are going to be the same value, so we're going to get 2 times something. So I'm going to just write this as 2 times something. And if you do that on your calculator, this is not an easy one to do in your head. You get a 1.1071, something like that. So in the end, when I go through all of this here, I end up getting an overall phase. Those first 2 0 contributions, right, canceled one another. The 0 didn't do anything. I just get 2 times 1.1071 multiplied by a minus 1. So that's going to be a minus 2.21, which I'm going to also tell you in terms of a multiplier of pi, that's minus 0.705 times pi, something along those lines. But let's go ahead and do it as minus 2.21. So I'm going to come back to my graph, and I'm going to come down here 1, 2, right, and 2.21. So there's 2.21 negative. And just before 1, right, I'm going to get that value, something like that. All right, now let's go ahead and do just one more, and I think then we're going to actually have enough time to get, or enough data to get the rest of it. So I'm going to look at the angle of HJ, not 1 minus, but 1 plus. Just when I go a slight bit past that frequency 1 where the 0 was at. This guy's still going to be 0, right? And we're going to have some plus, and we're going to have some minus. And in this particular case, actually, I think we can do that part first, right? We're going to be having that vector come up there. It's still a half, and it's still 1. We're just a little bit on the other side. We're just talking a smidgen below and a smidgen above. You can make that as small as you want. You could make it 1/4. It doesn't matter. Either side of that, the limit on this guy is that from the poles, you aren't going to see a difference. So that piece is going to stay the same. It's going to be 2 times 1.1071. Nothing changed on that. The zeros, on the other hand, are going to be a little different. Remember, again, we're looking for just a point slightly above the other, okay? The 0 from below, still pointing up. Whoops, let's do that in green. So that 0 from below is still pointing straight up, right? So we still get that pi by 2 that we had before, right? What happens with this other 0, though? Previously, it had been pointing down. Now it's pointing up. So it's no longer going to be minus pi by 2. It's going to be pi by 2. When you pass through a 0, right, you are going to go through a change in phase by pi. That pi is like a sign change. And I just want to go back to the magnitude response to try to see if we can explain this. Think about what's happening in this magnitude response. You could have had like a gain 2 here. It hits a 0. And if we didn't do this as like an absolute value, you might have seen it going down something like this, right? It became a negative number instead of a positive number, right? We hit that 0 and it went from like a positive number to a negative number, or vice versa. That's a 180-degree phase shift. When you pass through a 0, you get a 180-degree phase shift. That's what we're seeing here. And I'm just showing both sides of that exchange. So if I go through and I do all that calculation, I can go ahead and do it, and I'm going to get pi minus that, well, 0.705 pi, right? And if you do that calculation in this particular case, you're going to get 0.9273, which we could write out as being 0.295 pi, which is pi away from the previous one. And so I don't know if it's working good here, but I can say they're different by pi, right? Those two guys are different by pi. All right, so let's go ahead and plug that guy in as well. So I go through the transition of the 0. So we were just a little to the left of 1. That was before we hit the 0. We go a little to the right of 1. That's when we are going to be past the 0. And we had to go through a jump discontinuity of pi rads per second. We're going through a phase change of pi, and it's going up to about 0.3 pi. So if I come down here, and then this was about 1, and then that was about 2, and we're about a third pi, you're talking something like this. Okay, so what are we going to get in this? I know that this phase had to be something that transitioned from 0 all the way down to minus 2.21 over that first 1 rad per second. So we're going to get something like that. It hit that 0, went through a pi change, and then it continues on that, right, till it hits that asymptote of 0 in this particular case. Now, I probably messed this up, but I'm going to correct it a little bit. I know that whatever the slope was here, right, it better be the slope there. And for me to be hitting out asymptotically there, which takes a long time to do, I probably got some mess up in this first part. So let me get that cleaner and make a better guess on this. It's probably going to be more like this, where it's like concave up, something like that, because it's going to come out now with this slope here hitting that slope right there, which is kind of what I want. It just went through what? That's a pi change in phase. Because phase has to be an odd function. And that, again, comes out of the symmetry, that comes out of the symmetry of your pole zeros about that horizontal axis. The phase has to be odd. You can go through and prove this to yourself by repeating this same set of exercises, but do it at -1, just a little before it and a little bit after it, something like that. And you should see this set of negative values of the ones we just computed do. I'm going to just go ahead and use the knowledge that I know this thing has to be an odd function. So this guy is going to go 1, 2, 2.2 something, right? So this is like a 2.21 here, and it's eventually going to come back here at about 0.3. So I didn't do a good job of putting that in there, but that's like 0.3, whatever the case may be. Getting a little crowded here. Let's just leave that label off. So this is going to be coming something like that, and then it's going to go like this asymptotically towards 0. So even though our first values, 0, let's do that in blue, 0, 0, and 0 all seem pretty boring, it turns out this thing actually has a pretty rich phase response, right? It has a pretty rich phase response going on in there. Now, again, this is something that we did using a measurement of angles. Those are a little harder. They're not quite as easy. It's not a ruler one. You'd have to get some sort of a angle measurement or use your calculator. So I think it's easier to do the magnitude response, but the phases can still be measured. You can mechanically measure those angles, and you add and subtract those values, and you find a quick sketch to this. We will verify in the recitation these values using MATLAB. That's it for now.